We're starting with a lot written up there because I believe we had a significant portion of this already evaluated for the E2. So when we broke down the elimination reaction, we said what things happened. Okay, the big conclusion that I said that we could kind of draw through is it's really only two things happening. It's the breaking of that carbon-hydrogen bond and the breaking of the leaving group bond. Okay? Those two in conjunction at that same time is what's allowing for the formation of the pi bond. Okay? But really all that's happening is we broke those two sigma bonds, that built charges next to those carbons, resonance a la pi bond. So we don't have to evaluate the pi bond as an extra step that's happening. It's actually happening internal, which means that we get the same kind of thing as we had for substitution, 3 different ways that we could possibly combine those pieces. Okay. Once we've looked at those, I decided to go through and look at the situation for the E2 where everything is happening at the exact same instant. So we are breaking the leaving group bond at the exact same instant that we break the carbon-hydrogen bond. So if we look at our mechanism, that's our red arrows. Our base comes in, breaks the hydrogen, at the same time our leaving group leaves. So we get 3 curved arrows in this mechanism, okay, all in the exact same step. Which way do I want to go? Let's look at our energy diagram. So we start with reactants, and what do we end with? Products. How many intermediates have we formed? None. There are no intermediates. You'll notice there's that thing with the double daggers in the middle. Okay, we can kind of ignore that. It'll come back here in a second, hopefully. Okay. That's showing what's happening kind of closer to when the reaction actually occurs. Okay, but really we have reactants. The end result is we have products. That is one single step. And that one single step is why students will often refer to this reaction as E1. It's not a one-type mechanism. Okay? It's a two-type mechanism because the numbers aren't referencing the number of steps. They're referencing something else, okay, which we'll get to in just a second. So first I want that back. Okay, so if we looked at our energy diagram, we have our reactant, and then we form product. Should our product be higher or lower in energy than our reactant?
Higher.
Okay. Since David volunteered the easy question, or the easy answer, the rest of you get the hard one. Why? Why should it be higher in energy? Okay, so there's an interesting suggestion. Didn't see that one. That's what I get for balancing an equation. Okay, you're referencing the charge in the product of our leaving group. Fair. My counterpoint, we have a strong base. Also equally negative. So I like where you went. I disagree.
Is it because there's no S characters in the...
Indirectly, we could go with more S character. I think there's a more obvious thing. How many of you see hybridization and go, oh yeah, that's obvious? Okay, so don't use that argument. The product has a pi bond, which is getting towards your hybridization argument. Pi bond is made with p orbitals as opposed to hybrid sigma orbitals or sigma type bonds in our starting material. The pi bond is higher in energy, which means our product is higher in energy. So if we look at our energy diagram, we're going to have a single hump in it because it's only happening in one step. Okay, so single hump. And our product has to be higher in energy than our reactant, which means the reaction is endothermic. Okay, which kind of leads to one of our big summary points on the far right. We didn't talk about temperature with substitution reactions. We do tend to talk about temperature for elimination reactions. They almost always involve some form of heat. Okay? And it's ultimately stemming back to one thing in our reaction. It is the breaking of that carbon-hydrogen bond. Is that an easy bond to break? No. Why not? It's a nonpolar bond. So in one case, we can add a strong base to try and forcibly remove that hydrogen. In another case, we could just add heat. What is heat going to do?
Make it easier.
Why does it make it easier to break the bond? What happens when you heat something up?
Reacts faster.
Why does it react faster?
Molecules move faster.
The molecules move faster. We're causing bond vibrations. If I can give enough energy into that bond, it's going to vibrate so much that it literally breaks apart. Okay? And can be stabilized by something else in solution. I can form the pi bond, and there we go. Okay? So heat can be something to help this reaction along. So, next part. Let's take a look at that transition state. Because we want to think about that transition state and how this is going to potentially affect the end result. All right, what was our end result? It's the end result of all elimination reactions. Pi bond. Okay. Are there any interesting features that come out of pi bonds that we have to potentially consider? I know, nice vague question. We could potentially consider resonance because we have a pi bond. What else? Not RNS. We could worry about cis trans, or it would be CNE. Okay. That formation could mean that when we run through and do the elimination reaction, I could end up with just a trans product, or just a cis product, or both. Okay. This is going to be an added complication behind the reaction, one that I would need to be very careful of considering. When we go through and run the elimination reaction in the E1, we're going to form a carbocation. That carbocation can now allow any hydrogen to come in at virtually any angle. Okay? So we can get whatever product is most stable. Why are we going to be so concerned about the stability of the product? A little bit of a hint. It's a very little hint. It's a little bit bigger. It's an endothermic reaction. Because it's an endothermic reaction, that product energy is higher. To get the reaction to go forwards, do I want that product energy to be even higher? No. What do I want that product energy to be? As low as possible. That's going to help drive this reaction. Okay, more easily. Okay, so I'm concerned a lot about the energy of that product. Okay, that's going to be a huge impact in the overall success of the reaction. The more stable that product is, the more likely it occurs. Okay, the other thing to consider is what's going on in that transition of becoming the product. Okay. In the E2, this is all happening at the exact same instant. Our base is coming in and removing the hydrogen at the same instant that the leaving group is leaving. That is typically shown with these kind of, they're supposed to be dashed, but dots show up better. Okay, dashed lines. The leaving group bond is breaking at the same time, that our carbon hydrogen bond is breaking, the same time as our base hydrogen bond is forming. So all of those things are happening at the exact same instant. Okay? Similar to the SN2, the E2 has extra things to evaluate. In the SN1, okay, we had a little thing going in class. When I say SN1, you say carbocation. Because you all went in and did the SN2, you should have added an extra word to your vocabulary for the SN2. When I say SN2, you say backside attack. Why does it have to come in from the backside? Okay. Say that again?
Because you can have two negatives.
In the substitution, you've got the leaving group, which is leaving with electrons. And you have the nucleophile coming in with electrons. If they get near each other, they repel away. The nucleophile loses that argument every single time. So the only way the nucleophile can form a bond with that carbon is to be as far away from the leaving group as humanly possible, which is the backside of that bond. The exact same complication happens in the E2. The electrons coming in from the breaking of that carbon-hydrogen bond have to be coming in as far away from that leaving group as possible. Does anybody see an issue with how we've got this drawn?
Yes.
Yeah. They're on the same side. That elimination in the E2 case doesn't happen. That hydrogen has to be anti to the leaving group. If it is not anti to the leaving group, it doesn't happen. Okay? Some of that has to do with the hydrogen. That's kind of a thin argument, in my opinion. Okay? A slightly stronger argument, though also admittedly thin, because it doesn't evaluate molecular orbital theory. What is the base? What is the base supplying? Negative. Electrons. Okay? What is the leaving group leaving with? Electrons. If the base came in on the same side the leaving group was, we're going to get electron-electron repulsion. The base has to be coming in from the back side as far away from that leaving group as possible, which means the thing the base is attacking must be on the back side, okay, to allow this to happen. So the base comes in, shares its electrons with the hydrogen. The electrons come in, form the pi bond, kicking out the leaving group on the back side. This particular alignment, in a lot of cases, is directly anti. Where have we heard anti before? Newman projections. You remember the stuff we talked about way back when you're supposed to understand those structures? Here's where it becomes important. We have to have that alignment. So if you don't know what that alignment looks like, you can't answer the question. Okay? Or you end up guessing. Okay? There are subtle circumstances where we don't have to be perfectly anti, which is why we don't use the anti word in and of itself. We'll refer to it as anti. Okay? I refer to it as periplanar. I've also heard coplanar. Okay? Both of them are tying at the same point. Your leaving group and the hydrogen that's being removed must be anti to each other. Okay? So when we look at our considerations, we have to have this anti-alignment. And because the anti is the more important part, I would just write anti-alignment instead of dealing with the periplanar and coplanar stuff. Okay? By that same token, what if there's a bunch of crap out here? A bunch of carbons with a bunch of electrons. What does that do with the base? It could potentially repel the base. Okay? So we do have some steric considerations to evaluate as well when we go through and do this. Okay? So consider that. For the most part, those sterics play a relatively minor role because the E of our endothermic is playing a larger role. We want that product to be as stable as possible. Well, what makes a pi bond more stable? I'll accept that. What is this? Trans, as opposed to cis. Okay. Yes, that makes sense. We've got our groups as far away from each other as possible. That makes it more stable. So those are the only two possible states we could get, trans and cis. E and Z is also cis and trans.
Oh, R and S.
R and S has nothing to do with pi bonds. Does this pi bond have E and Z? No. Does this pi bond have E and Z? Whoa.
No.
Nope. Those groups are all the same. We wouldn't be able to distinguish. Does this pi bond have E and Z? No. Do all of those pi bonds have the same energy, the same stability? Okay, so we're getting a yes there. This pi bond has the exact same stability as this pi bond. Okay, we've got to convert here. Blue versus black. Why are you saying they're different? Let's stick with the easy question first. Not going to quite go there because it's not less bonds. So we could try and bring in charge delocalization. Doesn't work. The pi bond's not doing anything. There's no resonance. For your pi bond to react, what has to happen? Okay. Not only does it have to break, where do the electrons have to go? For me to hold a lecture, does it make sense if I only talk in the immediate vicinity? Does that work well? You have any idea what I'm saying? Okay. So, okay, not the immediate vicinity. Where do the electrons have to go? Elsewhere. They have to go outside the structure. What is the difference between this carbon and this hydrogen? So you're thinking too hard. What do you got, Raph?
Wait, you said it was
This carbon and this hydrogen.
The hydrogen can only form one bond.
The bonds are already saturated, so I don't quite accept that one.
One's carbon, the other's hydrogen.
Okay, so there's a nice easy answer. One's carbon, one's hydrogen. Yes, phenomenal. What is the difference between carbon and hydrogen?
Oh, the electronegativity.
Electronegativity isn't a bad argument, but there's a bigger, no pun intended, argument that happens before we get to electronegativity. Size. What is size? What makes the size of the atom? Electrons. This carbon has more electrons than that hydrogen. Why would that be an issue? If this pi bond breaks, what does it have to get by? Electrons. What is the pi bond? Electrons. In this case, the pi bond needs to break. It has to get beyond the shield of electrons on the outside. What has to happen here? There's less electrons. What does that mean? Black one is
More stable.
more stable. It's less likely to react to the outside world because it's more stabilized. Okay? This argument is very hand-wavy at best, but it gets to the point that we need. Okay? More substituted double bond. Okay? So a more substituted pi bond is a better thing for us. Okay? But what if it's not an anti-alignment? Which is more important, the anti-alignment or more substituted? When we talked about stability, what was the first thing we talked about? Charge, then size, then electronegativity, then resonance, then induction. Which was the most important? Charge. When did we talk about charge? First. Do you think maybe we've been revealing information in this sequence for a reason? Yeah, Tyler agrees. Yes, probably. He's a sneaky bastard that way. Yes, anti-alignment is going to trump everything. You have to have that anti-alignment. Otherwise, the rest of the stuff doesn't happen. Okay? So we do have to watch out for that more substituted pi bond. We want that, but we have to have that anti-alignment to force it. Okay? And then we just jump straight to our product. Well, cool. Well, could we bring the substrate into this? Right? The substrate is talking about the substitution patterns, and in particular, the substitution patterns where the leaving group is. If those were hydrogens versus carbons, what would that do to my substitution pattern? Say they were hydrogens. What kind of pi bond would I get? Okay, and if we can even just ignore out here, I don't really care. Ignore. There's our pi bond, right? What's the substitution on that carbon? I knew you didn't like that word. Should have asked.
What is substitution?
There we go. What is the substitution pattern referring to? Non-hydrogens. What is our substitution pattern at that carbon? Zero. There isn't a substitution pattern. We can reference the other carbon. That's part of the pi bond that has to be there anyway. Okay? So our substitution at that carbon is 0. There isn't one. Would that be a stable substitution pattern? No. And maybe you're just doing that because it feels like I do that too. But I'm gonna go with no. No, that's not a stable. What if instead those had been carbons?
Now it's secondary.
Now it's a doubly substituted. I don't want to use primary, secondary, tertiary because those are referencing sp3 atoms typically. Here we're moving into pi bonds. Right? So it's doubly substituted. So what happens if we backtrack this out to our halogen? What kind of halogen do I now have back to our primary, secondary, and tertiary? This one would be tertiary. The tertiary produced the more substituted pi bond. So tertiary leaving groups are more stable, or will result in more stable products, which means when I run an E2 elimination, what do I want for my substitute? Dude, that was not an eraser. What do I want for my substrate? Tertiary is better than secondary, better than primary. Because you've all studied the notes that we made for the SN1 and you made your own notes for the SN2. Okay, we missed the SN2. Let's go back to the SN1 because you at least studied those. What was our answer for the substrate for SN1? Reviewing our notes is okay, but ideally it would have been like, I studied it, I know that answer. Because the exam is next week. SN1 favors tertiary. Is that going to be a potential issue? Yeah, if I look at just the substrate, nothing else, the substrate, if it's tertiary, could do an SN1 reaction. What could it also do?
E2.
It could also do E2. So I have to be thinking about that when I try and process these pieces out. Okay? In red font here, because, sorry, go ahead.
Seeing as SN1 is exothermic, so can you start getting to the point where your SN1 starts creating an E2 because now it's creating heat?
So
Worry about that.
don't layer in
Okay.
the E2 yet because there's a larger issue there with the E1. Okay, and where that difference is going to come in is when we move to the next step, actually, as our big differentiator. Font color here for the base, I'm using red. Did I use red for anything else in, say, the SN1 reaction? I know you guys don't have colors, but because you went back and reviewed the notes and rewatched the video on the SN1, you remember what color I used for the nucleophile in the SN1. I use red. Why am I using the same color? Nucleophiles can act as bases. They're very hard to differentiate. That's why there's a supplemental video that goes into the exact details behind them. Okay? They are very difficult to differentiate. Okay? So in the elimination, I'm talking about it acting as a base. Note right up at the top, what does it say? What if nucleophile is not present? A base could be a nucleophile. Okay? So this is a site of confusion on looking at that secondary material and deciding is it a base or a nucleophile. And you will have that fight. Okay? But if we're now running under the elimination, we're changing it to a base. What kind of base do I want? Fair enough. I kind of missed this one. What did you guys say?
Strong base.
Strong. Is that different from our SN1? Because we all reviewed those notes.
Yes.
In the SN1, they want weak, not bases, nucleophiles. SN, N for nucleophile. Notice this says E2, not EN2. Do I want a nucleophile in an elimination? No, because if I have a nucleophile, what happens? I'm going to do substitution. Okay? Here's our differentiator. So to your argument, could an SN1 start generating enough heat that an E2 comes into play? Not really. Because for the E2, not only do I need that tertiary substrate, I also need strong base. And because the SN1 does not use a strong anything, I'm not going to see the E2 become an issue.
All right.
Okay? Why does it need to be strong?
You have to break that carbon-hydrogen bond, and it's a difficult one.
Why do I have to break that carbon-hydrogen bond?
Because if you don't break it, you don't get a pi bond. You don't have those electrons.
But in an E1, I don't need a strong base. So the E1 is going to mimic the SN1. It's going to come in as weak. What is the point of breaking that carbon-hydrogen bond? Yes, the formation of the pi bond is part of it, but as we said, the formation of the pi bond isn't our big answer. It's what? You're differentiating with nucleophiles and bases? Different question.
Is it so carbon can keep its octet?
What's the point of forming that pi bond? What's the end result? So as a hint, there are 3 steps, and you've discussed 2 out of those 3 and left the 3rd one off. The leaving group leaves. Why does the leaving group leave?
Because it was kicked out.
Because it was kicked out by the carbon-hydrogen bond breaking. Okay? It is that base that's causing that to happen. If I can't break that hydrogen off, I can't kick out the leaving group. I don't form the pi bond. Okay? In the E2, because it all happens at the exact same instant, I need a strong base to initiate that. Okay? How do I know I need that? Okay? Well, that need is something that's important. I wish there was a way that we could discuss a reaction's needs to allow it to happen. And to allow it to happen at a reasonable, I don't know, rate. Like a rate law? That's an interesting suggestion. I like that suggestion. If we took a look at a rate law, the rate for this reaction will be rate equals lowercase k, our rate constant, times our substrate concentration, which isn't new because that's exactly what we had for the SN1. Okay. Why is this one so different? The concentration of base is now also factored into this. The stronger that base, you might say, well, how does that affect the concentration? That's because, did they tell you in your rate laws, those actually aren't concentrations. Did anybody tell you that?
No.
Oh, well, that was mean. They aren't concentrations. What it is happens to be heavily tied to concentration, but it's not concentration. It's called activity. Okay? That's what's showing up in your rate law. The strength of a base happens to also be directly tied to its activity. So if I make a base stronger, its activity increases, effectively its concentration increases, ish, okay, as far as the rate law is concerned. Okay? That is a challenging concept to deal with, which is why they don't tell you about it. Okay? Because if they tell you about it, then what are you going to do? Well, how do I calculate it? Don't freaking ask me that. I don't know. Okay? All I know is that it is tied in there. The strength directly ties to that activity symbol. Same thing with equilibrium constants. Those aren't concentrations, those are activities. Okay? So if we increase the strength of the base, we're effectively making this rate go faster. Okay? That's why we need a strong base. Which brings in an interesting point. What kind of molecularity would this reaction be? Bimolecular, cool. At least someone caught that word phrasing. Go all back to 152. You refer to reactions by their molecularity. This is a bimolecular reaction because how many things show up in the rate law? 2, and it happened to be an E2. That's why the 2 is there. It has to do with the rate law. Okay? Do I need a leaving group for this reaction to happen?
Yes.
Yes. Okay? So when we look at considerations, all the component pieces, leaving group, I would say yes. It needs to exist. Okay? If you don't have a good leaving group, you'll have to make it a good leaving group. Okay? Solvent. For the eliminations in particular, the solvent becomes very tricky to deal with. Okay? I need a strong base. Name a strong base. Okay? OH minus doesn't work because I can't go into the store and just say, give me OH minus. What am I going to ask for? I'm going to ask for sodium hydroxide. What phase is sodium hydroxide? It's solid. How am I going to get sodium hydroxide to interact with this if this is a liquid and this is a solid? I'm going to dissolve it in a solvent. That solvent that I pick is water in this case because it happens to be the conjugate acid. Water happens to be a polar protic solvent. What is that proticness going to do to the strength of the base? It's going to neutralize it. It's going to weaken it. Okay? So we might say, I don't want a protic solvent. You get rid of the protic solvent, what happens? You don't dissolve your base. Okay? So the solvent term, when we're looking at our elimination reactions, is very sketchy to deal with because the solvent is almost always the conjugate acid of whatever base you're using. Because it is the conjugate acid, it by definition is protic, which would be counter to the base strength. That becomes challenging to deal with, so I would argue that you should pretty much ignore solvent contributions to elimination reactions, right? Because they are often misleading. Okay? So if we're going to get rid of some information, it might be nice if we brought something else in to replace it. What's that something else? Heat. Okay? The heat is going to be the piece that we use to replace it. If we see heat in our reaction, it's a tip-off that we might be going down the elimination path. It's not a guarantee, okay? But it does point us in that direction. How do we know we've added heat?
The contents are cooling down. Or
Upper left-hand corner, A goes to B. Did I add heat?
oh, delta.
The delta's one of our biggest tip-offs for heat. That's all I was asking for. Okay? Sometimes you won't see it as a delta written above. Sometimes you'll see it written as a delta below. It's the same thing. Okay? Sometimes you'll potentially also see this. Is that a delta? No. Did I add heat? Yeah? How do you know? Because it shows a temperature.
That's warmer than
Okay, so shows a temperature. Did I add heat?
No.
No. Now I'm removing heat. So what are we doing to decide that that 40 was adding heat?
Room temperature.
Room temperature is about 20 degrees Celsius. If we just want to keep it simple, either 20 or 25. Just memorize one of those two. It's usually like 22 and a half. Don't worry about it. Okay? So if you see a temperature larger than 20, you've added heat. Okay? Less than 20, you've removed heat. You're cooling it down. Okay? This is now our E2. We've now looked at both type mechanisms, 1 and 2, and substitution and elimination. You have the SN2 to do the exact same argument with. You have the E1 to do the exact same argument with. You should, again, go through and look at all of those details on your own time. If you want help, by all means, sit down with me in office hours and we'll go through it. Okay? But the rest of the slides we're now going to be jumping through are going to be looking at each of these pieces in kind of very specific circumstances. Kind of make sense? Okay? So, this was our elimination summary. okay, which was our initial breakdown. Here I decided to, break it really small, okay? Which gets us now into chapter 7, very, very briefly. These are all of the elementary mechanistic steps. They're either heterolytic bond cleavage, so breaking of bonds, or bond formation, making of bonds, or you're doing it both at the same time. Okay? So when we talk about our reactions, this is ultimately what we're going back to. We're now just combining these in varying states. Okay? For this first exam, you're expected to be an expert at all 5 of those. 6 of those. 6. The electrophile elimination bothers me. I think that's better called as an acid elimination. Yeah, just my 2 cents. Okay, the additions, the electrophilic addition, nucleophilic addition, and the nucleophile elimination, okay, you are responsible for knowing what those are. So if I show a reaction, you should be like, that's a nucleophile elimination. That's a nucleophile addition. Okay? But I don't expect you to be experts behind the details of them. Okay? Guess what unit 4 is? Electrophilic addition. There is no unit 5. So guess what all of next semester is? Really, those 2 in combination with everything above it, looking at different levels of detail and getting into more specific reagents that force those things to happen. Okay? So, when we look at the simultaneous, bond cleavage and bond formation happen simultaneously. So if we take a look at the substitution reaction, okay, we are forming the bond at the exact same time we break the bond. So the iodide is attacking at the exact same time as the bromide is leaving. Right? When we look at that reaction, just the reaction on its own, what tips do we have that we should be doing this all at the same time? Say that again? The solvent. Acetone. Are you responsible for knowing the structure of acetone? Yes. That is one, if you ask me, I'll give it to you. What can you tell me about the solvent of acetone? Okay, it is polar aprotic. Does that favor the SN1? No. So this says not SN1 right now. Because none of you went back and reviewed SN2, or at least brave enough to say that you did when no one else did, okay, you can't tell me it's SN2 yet. So all you can do is tell me it's not SN1. Okay? Which is fine. Knowing the negative is also as equally valid as knowing the positive. What else should we look at?
There's no pi bond, there's no E bond.
Okay? No pi bond. Which means? Not an elimination. So for the bulk of this test, that's good. Okay? Substrate. We look at where the chemistry is happening. How many carbons is connected to that one carbon? 1, so this is a primary substrate. Does the primary substrate work for an SN1? No, so it's not SN1. Okay? Arguably right now, you should probably be like, I don't need to worry about anything else because I've covered the majority of things. I know it's not elimination because there's no pi bond. Right? It's not SN1 because it's primary. It's not SN1 because it's polar aprotic. You could pull the trigger now and say it's probably SN2. Okay? Now you could go through and add arrows. Okay? Majority opinion isn't good enough. What else do you need to look for? You need to be looking at your nucleophile. And when you look at your nucleophile, it's typically written as shown right now, NAI. Everybody looks at it and they go, what kind of nucleophile is that? I know what you're saying. And no, that's not at all what people say. They look at NA and they go, oh, that's a weak nucleophile. So why? Because it's not charged. That's an ionic bond. There absolutely is charge. That's because it's an ionic bond. Okay? You need to be processing that level of detail. Since it's an ionic bond, we have a negative iodine. Negative means strong. Because it is strong, what does that mean? 2 type. Well, you might say SN because it said not elimination. Why do we say not elimination? There's no pi bond. And you know there's no pi bond because you look at your reactant and you look at your product. Oh, crap. How do I know it would be SN now?
There's no strong base. There's no base.
Okay. To do the E2, I needed a strong base. I minus is strong. Is it a base?
No.
No, because if it acted as a base, it would form
Hydroiodic acid.
HI, for those of us that don't want to actually use nomenclature, which is
A strong acid.
a, by definition, strong acid. Which thereby means that could only act as a nucleophile. With that information, I know I'm running SN. Okay? Remember, this exam, I can give and take away all sorts of pieces of information. Don't rely too heavily on just one piece of data to get you through a question.
So if it forms a strong acid, it can't.
If it forms a strong acid, that step was a bad step. You shouldn't be doing it. Okay? Make sense? I'll accept that. Bottom one. Okay, let's go through and look at some of the notations in here. For the bottom one, this is just our general elimination. Because we're told it's an E2, what has to happen? You have to have a strong base. Is that a strong base? What the hell is M/H? For those of you that read ahead in the slides or even looked at the old slides that we had, maybe you could have asked. And to those of you that did, touche, good job. For those of you that didn't, why the hell not?
That's the side chain, correct? Or a hydrogen?
Why is M? M is not a side chain representation. M would be an R.
Main chain?
Say that again, Tyler?
A metal?
Metal. This is a metal or a hydrogen. How would that change my base? So a base with a metal, let's pick sodium, versus a base with hydrogen. How does that change the reactivity of my base?
That sodium base is an ionic bond.
The sodium base is a metal, non-metal. That's an ionic bond, which means
That's a negatively charged base.
that's a negatively charged base versus a
Neutral base.
neutral base. The negatively charged base would be a strong base. If I'm going to run an E2, which of these two bases should I be considering? The top one with the metal. What is that base reacting with? Hydrogen. So I want the base to attack the hydrogen. For those of you who want me to pause, shush your mouth for a second. It hurts me too. We remove the hydrogen, leaving group leaves, simultaneously we form the double bond. What could ever be wrong with that? We could even do this. There's the formation of the pi bond. All too common. Okay? Multitudes of problems with this one. Where do we want to start?
Orbital arrows, please.
Not yet. Okay. The hydrogen that I need to attack, and this is probably the easiest way to centralize all the problems here, okay, is say that hydrogen was a bad hydrogen. I'm not allowed to remove that hydrogen. The hydrogen has to be over here. Okay? Couple reasons for this. The whole point of the removal of the hydrogen is to stabilize the positive carbon. So the electrons in the bond need to go in to stabilize a forming carbocation. If we look at the blue hydrogen bond versus the leaving group bond, those bonds are never in the same plane. What does that mean? The electrons in that blue bond can never be used to stabilize that purple leaving group. The electrons are in perpendicular orbitals. Because they are in perpendicular orbitals, they never interact. For those of you being like, I can't quite process it because I can't see the orbitals. Number one, that's a huge step because you're like, I can't see the orbitals. Okay, for those of you being like, orbitals? That's the hard step. Okay, that's the really hard one. So don't stress on that so much. Just realize you can't pull from there. So what's our tip-off that we could use to memorize this? Okay, Christian gave us an awesome hint on this. He said the hydrogen had to be that purple hydrogen. So let's take a look at that purple hydrogen. Okay. I want to number my structure. I want to label that structure. I know the leaving group has to leave. Okay. The location of the hydrogen in the leaving group, I want to be able to reference them. Would they always be at position 1?
No.
2?
No.
No. So the numbering system is now kind of out the door. I know we use 1,2 hydride shifts. Just ignore that. Okay. So we had to come up with a new nomenclature system to reference the relative position of those groups. Okay. I know the leaving group bond is the easiest bond to break, so I'm going to start my nomenclature system there. If I can't use numbers, what could I use to reference that position? Letters, and I could call it A and B and C, except the problem with that, do we have a letter B? Like on the periodic table? And C? Yeah, so A, B, C doesn't work. I like the idea, though. That's such a good idea that I'm going to, instead of using the standard Roman alphabet, Roman? Just trust that. We'll switch to the Greek alphabet. And I'm going to reference the position where that leaving group is, and I'm going to call that alpha. Where's the hydrogen located then? The beta position. When I go through to do this elimination, the base comes in, removes the hydrogen, the electrons swing down to form the pi bond, the leaving group is ejected, and I've now done an elimination. In that elimination, I eliminated a hydrogen from the beta position from where the leaving group was. So I could reference this elimination as a beta elimination. So if you hear reference to the beta elimination, it's to help accent the fact you have to pull the purple hydrogen, not the blue hydrogen. Why can't you pull the blue hydrogen? Orbitals. If you don't like that answer, then beta. If you like the orbital answer, then talk to me after class and we can look at orbital pictures. When are we done? 45.
12:45.
45, okay. Make sense? Okay. So there's our elimination. This is happening all in one step. How do we know it was happening all in one step?
We have a strong base.
Okay. That's actually not how we knew that. Okay, we knew that because the top of the slide says SN2 until we eliminate SN or the E2. So how do we know now that it's an E2 elimination? We have a strong base. That strong base is what's tipping us off that we're doing the E2. Okay? Could we use the substrate? Would we expect this substrate to be a good one for the E2?
Not terribly,
Not really. Why not?
because it's only a primary. Well, assuming that the leaving group is
It's not primary. It would be, well, depending on where you're looking. If you look at the halide, it's a primary halide. And primary halides, not great for E2. Okay? We could also look at the product. The product is mono-substituted or singularly substituted. Not great for the formation of the product either. Okay? So as an example structure, it's nice and simple, but it also doesn't accent the highest utility of this reaction. Kind of make sense? Okay. Because this is an example, it's supposed to represent the E2 as best as possible. Is this orientation of the leaving group in the hydrogen particularly a good one?
No.
No. Could we fix this so that it looks a little bit better for our own notes?
Yes.
Yes. How would we fix it?
I would rotate that sigma bond so that it was forming that like half hexagon. Yeah, there we go.
That better represents what? The anticoplanar alignment. Planar alignment. Okay? So that's our basic mechanism for the E2. Okay? One that we talked through already. Okay? For the SN1 and E1, these are stepped mechanisms. Okay? Instead of doing everything at once, we're breaking them into smaller steps. The very first step is heterolysis. Okay? We're going to break the carbon leaving group bond first. Why break that one first? Because in an E1, don't I have to break a carbon-hydrogen bond? Why do the leaving group bond first? Carbocation isn't a bad jump. You're saying, oh, I memorized SN1 is carbocation, one type is carbocation, so it's got to be a carbocation. Yes. Step back. Give me more reason. Why should I break the leaving group bond and not the carbon-hydrogen bond first? What's that? Well, you're still going back to the same explanation, which is I memorized the one type has to do that first. I want to know a reason why we should do that, particularly for the E1, why we should break the leaving group bond first and not the carbon-hydrogen.
It's a polar bond.
It's a polar bond. The carbon leaving group bond is an easier bond to break. That's going to be the easiest bond, first thing to happen. After that, we can deal with the acid-base reaction. Is that a stretch? Never mind. So we will break our leaving group bond first. That first step is now a heterolysis. Okay? Because Cardi breaks down the different mechanistic steps, you are responsible for acknowledging that as a heterolysis. Most textbooks do not make reference to those mechanistic steps. Okay? So if you aren't using our textbook, I hope you're taking good notes and you've watched that video on chapter 7. Okay? What would the end result be of just that arrow pushing? The carbocation. There we go. I've got a carbocation. Did I do it right? You're laughing and shaking your head. No. I cannot stress enough how many times students do something exactly like this. Okay? And it's not, you're just like, well, the rest of the structure's there. Oh, I don't need to worry about it. You still got to freaking draw it. Okay? R. Okay? Now what happens? Say that? We could reference this potentially as a secondary carbocation because, and maybe what you're referencing is if it's secondary carbocation, what could happen? We could do some kind of rearrangements, which could be hydrides, not hydrogen, or carbons, or other groups entirely. Okay? At this point, we aren't trying to focus that deep into this, okay? But we do have to watch out for those high energy intermediates. They can do all sorts of side things. What else could happen to this? Is our carbocation stable? What does it need? Electrons. Where could it get electrons from? Okay. It could get it from the chloride ion, which is acting as a nucleophile. Okay. What kind of reaction did I just run? Mechanism. Coordination. When I combine a heterolysis with a coordination, now I have an SN1. Make sense? Okay. That was a carbocation. What could I do to stabilize that carbocation? Form a pi bond. Where does it get the electrons?
From the hydrogen.
from a beta hydrogen. And I can form the pi bond. Okay? That step is now what kind of mechanistic step? It's an elimination because we formed a pi bond. Fantastic. What did we eliminate from the structure? This is where I have a hard time with Carty's description. I understand where he's going from. You're eliminating an H+. I would argue that we shouldn't be calling that an electrophile. We should be calling that an acid. So I would call this an acid elimination. Ultimately, can that species accept electrons?
Yes.
Is that the definition of an electrophile?
Yes.
Yes. That's why Carty's using it that way.
Okay.
Okay?
So you need a base in there?
So we could bring in a base. Do I care about the strength of the base?
No.
One type mechanism, I'm only concerned about one species. What's the one species for my one type mechanism?
Substrate.
The substrate. So I don't need a strong base. Because I don't need a strong base, I could use a weak base. Okay? So I would look to see what else was in solution that could possibly do that. Okay? It's usually the solvent. Okay? Anything with lone pairs.
So ammonia maybe?
It's usually ethanol or water.
Oh, okay.
Okay? Kind of makes sense? Because we're using a weak base, is that hydrogen going to be easy to rip off? Is the base going to be, oh yeah, it's easy to take me away?
No.
No. So how could I help that weak base break that bond?
Heat.
Heat. Okay? So when we talk about heat, for the E2, it becomes a little bit less important because I'm using a strong base. For the E1, I'm not using a strong base. I typically need something to help force that off. That's where heat really comes into play, is with the E1. Make sense? Question? Nope. Okay. So, do we really care about the mechanism? Okay. My opinion, I tend to be more knowledge for the sake of knowledge. So philosophically, yes, I care about the mechanism. I care why it works because I just want to know why it works. Okay. Most students don't have that level of commitment, maybe. I don't blame you. Okay. So do we care about it chemically? All right. Well, let's go through and take a look. First two reactions, what kind of reaction are we running? Substitution. Last two reactions. Elimination. So do I care which mechanism I'm running?
Yes.
Yes, because in one case I end with a pi bond, one case I don't. That's kind of a big deal. So yes, I care about the mechanism. Okay, but between that, do I care SN1 versus SN2? And we might say not really. And why might you say not really?
You've ended up with the same product.
Same product, right? Exact same product. What can you tell me is special about the structure that I picked? It is chiral. Whoops. And if we were to add that layer of detail there, I'll give you the SN2, becomes dashed. The SN1, you should be able to tell me, because again, you went back and reviewed those SN1 notes. And in those SN1 notes, what did it say happens with your product? We get both. I get both the wedged and the dashed. Do I care which mechanism? Yep. Okay. If the dashed one cures cancer and the wedged one kills you, an SN1 reaction, not a good option. Okay? On top of which, if I only want the dashed, the maximum yield I can get for an SN1 reaction would be 50%. That's a piss poor yield. Okay? And that doesn't even take into consideration like technique stuff, which as you've all experienced in lab, has no impact on your yield at all, right? First time doing an experiment, you just get perfect yields. Okay? So we really have to be cognizant and thinking about that. When we go through and do the elimination, we're going to end up with a similar situation. In the E2, we had to have the anti-alignment to force it, okay? Which means when we get our product, we tend to get one product, okay? Favoring however the anti-elimination occurred. This becomes really difficult to draw because we have to make sure the starting material reflects that. If the starting material doesn't reflect that, it doesn't matter what I draw, they're going to look all the same. Okay? So when we go through and do these mechanisms, we get different results depending on which one comes out. This is why Cardi built out his little table. This helps you to kind of differentiate which mechanism you're doing. Because if you know which mechanism, then you can zero in and just do that one mechanism. Do you all agree once you're told what mechanism it is, it's okay?
Yeah.
Couple head shakes, yes. If you're told just tell me what it is, that becomes a lot harder, right? Okay? Because now not only do you have to try and figure out which one it is, you then also have to stack in all those other extra considerations. Okay? So that's why Cardi built out the table. Genius idea, though I don't understand the point of a leaving group. Take a look at the leaving group row here. SN1, check. SN2, check. E1, check. E2, check. How does looking at the leaving group evaluate at all whether I do a reaction or not? It doesn't. That's pretty freaking stupid in my opinion. Okay, why is it there? Do you need to have a leaving group?
Yes.
Yes. Check. Now I can move on. Okay? The other one that bothers me is strength and concentration. Looking up here, is the strength obvious? No. Do you have to do some thought process behind it? Yeah, so that strength one becomes a little bit challenging. Ideally, your processing is ionic bond. Chop the sodium off, negative, which means strong. Check. Because SN2 favors the strong. Okay? Concentration. What is the concentration of starting material in that reaction?
No idea.
None of our reactions show concentration. Okay? What I think he's trying to get at with the concentration is more like the idea of the activity, which is really getting to the strength, so I think it's just confusing and shouldn't be put in there. Okay? So what I went through and did is modified it according to things that I think about. Okay? If you like the way Cardi presents, fantastic, use that. If you don't like the way Cardi presents those things, then you can use my way. Strong nucleophile, strong base. Notice I've differentiated those, nucleophile versus base. I wonder if there's a way to differentiate those. Oh, that's right, I made a video for you to watch, that you all watched, that now allows you to tell the difference between a nucleophile and a base. Yeah, there's some head shakes. Yeah, cool. You're starting to get sick of me referencing these things. Okay, prove it to me. How do you differentiate between a nucleophile and a base? Fair enough. Good answer. Bases will attack a proton. Nucleophiles attack everything else. So when you look at a structure, how do you know it's attacking a proton versus anything else? I think I like what you mouthed. I think I saw, I don't know.
It's attached to a hydrogen.
In the product. Do you have a product? Damn it.
You know,
Where are hydrogens?
Next to carbons.
Okay, where are carbons? Next to hydrogens. Next to other carbons. Where are hydrogens always?
On the outside.
On the outside. Where are things not hydrogen?
On the inside.
On the inside. If we go through and take a look at this, a nucleophile has to react with something other than hydrogen, which means it has to react
On the inside.
inside the structure. This is why you need the little TIE fighter to fly in to get into the inside. You can't use a freaking Death Star to attack a Death Star. It doesn't work. I couldn't remember the other things. Star Destroyer. There we go. Whatever. Okay? We need the little TIE fighters, X-fighters, things, flying small vehicles to get to the inside to be a nucleophile. So nucleophiles tend to be small. If I want it to act as a base, do I want it to get inside?
no.
No, I want it to react where? Outside. So what could I do to make sure it can only act on the outside? Make it big. If it's now big, it can't get to the inside. What if it's small? Could it still get to the outside? Yes. Okay, so small things aren't necessarily not bases. Oof. Okay? But large things are definitely bases. So you can use a size differentiation of your structure to help you kind of needle those two out.
Most of your small things won't work anyway, right? So you've got
Like a negative carbon, negative nitrogen, negative oxygen. All of those are relatively small. Yeah. Well, you could have a negative hydride or hydroxide. Hydroxide is
Fairly small, okay.
could be a base or a nucleophile. Okay. Leaving groups I made as a tiny little place just because they're dumb. Substrate. Well, let's try this. Strong nucleophile. Which one wants a strong nucleophile? What do I want for the SN1? Weak. Okay. Base. Which one wants a strong base? What is the E1? Leaving group. Substrate. What do I want for SN1? Good thing to jump on is carbocations. The general trend that people tend to remember is tertiary is better than secondary. We can ignore primary and zeroary. The one thing that becomes really important on referencing carbocations is tertiary the be-all, end-all of stability of carbocations.
No.
Nope, because we could also do allylic, and I know where you're going with that, too specific. Broaden that. Why are allylic more stable than tertiary? Resonance. Resonance can be used to stabilize the carbocations. Okay? So officially we can do resonance out front. SN2, what do I want? 0 is better than primary, better than secondary. Tertiary, not part of it. Okay? The word, backside attack. E1, what do I want? E1's going to match SN1. Resonance, more than tertiary, more than secondary. This is all because E1 gets carbocations. What happens with the E2?
Here's SN2.
No. Don't worry, don't feel bad. It's not like we just talked about it like 20 minutes ago. Shit. Tertiary, more than secondary. It's the substitution patterns. Primary. We won't include zeroary on it because zeroaries can't form pi bonds. You need 2 carbons to form a pi bond. Solvents. SN1. I'm just going to write protic, but no, I'm not. Polar protic. SN2. Polar aprotic. These ones are misleading, so I would say Na for your eliminations. Heat. It's really a big driver in our E1s. Less so in our E2s, and not as important in our substitution. So now when you look at a reaction, you just have to evaluate. The nucleophile, well, it's strong. Check next to the SN2. Okay? The substrate, well, it's primary. SN2. Okay? At that point, you've got 2 out of 4 categories. You're probably good to just say it's SN2. Not a bad idea to check the solvent and look for heat. What if it says strong nucleophile, primary substrate, polar aprotic with heat? It's still SN2. Just because there's heat doesn't mean you're doing elimination. Right? You're looking for the majority of these stacking out. For those of you that couldn't keep track of all those check marks in your head, that's okay. Go back, rewatch the video. We're at minute 69:38. Okay. Reaction rates, conclusions. We already kind of talked about these, so this is okay. When you look at a rate, those orders have to be proven experimentally from 152 Hopefully you remember that. If we add those orders up, we get the order for our reaction. The superscripts are the math behind this. What is the numerical mathematics that makes that equation work? The order is our chemistry trying to make sense of the English. Right, that's chemistry trying to make the math understandable using English. Okay? So that's where we get some kind of confusion between this. Chemistry is this language that's trying to explain what's happening in mathematics using English. Well, because English is a universal and lovely, well-organized and formatted language without any exceptions, that makes our job that much easier. Okay? For those of you who look serious, that was a joke. Our reagent orders. Okay? So our order of our reagent, if it's zero order, it's not there. First, it's involved in the reaction. Second, it's super involved. Third order means it's all me. For that reaction to happen, I need 3 of those molecules and that's it. Which means the rest of the world has disappeared. Why do I not get more than 3? How many dead people are there? A lot, okay. How many single people are there? A lot, not too bad. How many couples are there? A lot, the same as the dead and the singles? No, there's a little bit less of the couples. How many threesomes, successful threesomes, are there? Not very many. How many successful 4, 5? Yeah, non-existent. You can't get that many people together. If you can't get that many people together, guess what? You can't get that many molecules together either. Okay? So much so that when we look at organic chemistry, we ignore the third order. If we have a reaction where we think it's described by 3 molecules all interacting at the same instant, we disagree with that philosophically so much, the mechanism is invalid. So at no point should you ever show 3 molecules interacting with each other. Okay? That said, I'm sure somebody's gone out there and proved that you can do that. Okay? Super rare occurrences. As far as the class goes, first and second order. We could refer to these as the molecularities, which we already got. Non-existent, uni, bimolecular, the term moleculars we don't worry about. Okay? When it comes to rate laws, we could go through and look at our rate laws, and you may notice that the rate laws in these cases don't match back to their equation. Here it's second, but that one's first and that was second, whereas this one, wait, what? What happened? Isn't the rate law supposed to mirror exactly the chemical equation? I'm drawing arrows. No, the rate law doesn't mirror our reaction. What does the rate law mirror? The slowest step. Slowest what step?
Rate limiting.
Mechanistic step. This is why Chapter 7 was so important, looking at those mechanistic steps. That's what we're evaluating when we look at our rates for our individual reactions. That's why we could come up with a rate law from the mechanistic steps, and we couldn't do it from the reactions. Okay? Those rate orders have to be solved from experiment. Okay? If we go through to look at a mechanism, we could come up with the whole rate law for the whole thing by slow steps. This is what I did for Gen Chem, so don't stress necessarily about this. Okay? What we're concerned about is the slowest step in a reaction. The slowest step always controls the rate of the reaction. So that's where our focus is. For organic chemistry, most of our slow steps happen where? The first step. Okay? That's our driver. So as long as we look at that first step and have nailed that one down, we can dictate the rate for the rest of them. Experimental evidence. Given this, would you be able to calculate the rate constant? Please say yes. Good, then I don't ever want to have to ask that question again. Literally, I don't want to ask that question again. Okay? After that, what we start moving into is our background behind each of those mechanistic steps. That's our end of our 152 review. We are also done for today.